Again. So this lecture and the next one is about NLP. So this in particular, it's about deep learning for natural language processing. Yeah, since the whole course is about deep learning. So deep learning, I mean, NLP has seen great progress in recent years. There has been a lot of hype around uh, the things that we have been able to do, especially what deep learning has achieved for NLP in the recent years. These are some progresses that have been achieved. So uh, he says that humans prefer machine translation to human translators, which is like a huge thing. I don't know how, to what extent that's actually true, but it's like a really great achievement. Superhuman performance on many question answering data sets. So this is so the for those of you who are aware, there is this quad benchmark, which is just a set of paragraphs and questions and answers from those paragraphs, I think. And um, the ML model, or more specifically, the large language models, have been able to defeat human performance on these question answering data sets. So, specifically, these question answering data sets are, I mean, this particular task is just extracting the span of the answer in the question. It's not, I think it's not uh, inferring or anything from the paragraph. I mean, it's just directly extracting the answer from the paragraph. And language models generate fluent paragraphs. We have all seen so many examples of that in the past year and the year before. Yeah, not just paragraphs, even things like code, SQL queries and whatnot, things like that. Also, GPT-3 for example, has been able to generate very impressive things. Minimal specialist techniques needed per task. Okay. So this is old news for us. This is GPT-2. This is what GPT-2 was able to generate in 2019. So they gave this particular paragraph as a prompt to GPT-2, and the rest of it was generated by GPT-2. So one thing I noticed that was funny here was the Andes mountains are in South America, and the name of the scientist is also like a Latin American name. So I don't know if that's just coincidence or it was actually smart enough to deduce that. Yeah, that's just something I noticed in this. Um, uh, yeah. So what is a language model? Um, Language model is just assigning a probability to a text. What is the likelihood of this text? I mean, what is the likelihood of such a text occurring? I mean, not occurring. Yeah, such a text existing. Um, so you can't suppose you're trying to generate sentences. There are just so many infinite sentences possible, right? So if you're trying to generate sentences, you can't just train a classifier for that purpose. So uh, we factorize the distribution using chain rule. So given the first word, what is the probability? I mean, first word, what is the probability of uh, probability of any word being the first word, and then probability of x1 given that the first word is this, x2 given that the first word and the second word and the first word are these, and so on. So this is how you factorize it using chain rule. So now you have many manageable classification problems. So suppose you have a sentence which goes like this: the scientist named, and so on. What is the probability of the next word being unicorn? So this is how uh, the language models that we have work. So we give it some prompt, and then you ask it to predict the next word given these words. Um, so if the language model has seen lots of English text, it knows that if after their distinctive horn, so it's more, I mean, there is a good chance that the next word is unicorn, since unicorns have a single horn. So that, yeah, I mean, that's how language models work. It tries to predict the next word given the previous words that it has seen. And how do you do that? So um so here's where we use neural language models. So basically language models using neural networks. So this is like a basic way of a simplistic way of doing that. um so essentially what you're trying to do is you have the words that the words that we have seen until now, and using that uh, you make a context vector which embodies the meaning or the context of the sentence prior to it, and using that context vector you predict the next word. So I think in this one, uh, you have any neural network here which basically gives you a context vector from this sentence, and then you do some kind of similarity with all the words in your vocabulary. um, so word embedding matrix is basically a matrix with as many rows as there are words in your vocabulary, and each word has its own vector associated with it, and you just do a similarity and with the current context, and that's how you choose the next word. Yep, you do a softmax and you get the probability of each word being the next word. I'm just zooming it out a little bit. Then we have convolutional language models. Um, so here, again, each word is embedded as a vector, and you have the same feed forward network at each time step to predict the word at the next time step. And fixed length history means it only can only condition on bounded context. So convolution language model, it applies I think it applies a 1D convolution on your words, uh, and it has a fixed kernel size. So it could be something like 4 words or 5 words, I think, and it just moves that kernel across your sentences, across your sentence, and so as we know in convolutional models, there are some intrinsic assumptions and all. So something like locality is assumed. So there is only local relationships. So which is quite true in images, right? In an image, you won't have any connections between separate locations in the image. Like you have your suppose in a face you have eye at a particular spot. You don't, I mean, there is no huge relationships between different parts, but in a text that is not true. You can have relationships or interactions from the start of the sentence and to a word which is much far away. Um for example, if you have a name at the beginning of a sentence, then the pronoun that occurs, say 15 or 16 words away, it depends on the gender of the first word. So you can have very long relationships, which is not possible in convolutional language models, because there is a fixed window, fixed length history. So when you are generating the next word, you can only see the last 4 words. Yeah, last 4 or 5 words, whatever the length of the kernel is. Mm, yep. So RNNs kind of solve that problem. So if you're aware of language models, I mean recurrent language models. Um, so in this whole lecture, he does not go into the depth of any of the architectures. He just gives an overview of it. In the next lecture, we have code, so I think that will be much more interesting. So here, he just explains what language models are. So in general, language models, they maintain a hidden state, and this hidden state gets updated every time you see a new word. So in a way, RNNs are the most natural seeming uh, neural network. I mean, natural seeming way of I mean, of taking in text, uh, because it's yeah, it seems like the way humans also understand text. So we read from left to right. So similarly, it maintains a hidden state, and each time it sees a new word, it updates the hidden state, and and uh, and theoretically it actually um, it remembers the entire thing from the start of your text, your paragraph, whatever. It remembers the whole thing. So yeah, that's how it has unbounded context as opposed to the fixed length history which CNNs have. Context is compressed into fixed size vector at each time step. So that's the hidden state of your RNN. But practically what happens is gradients tend to vanish with long context. So the example which I said earlier, if you have the name of a person at the start, say Henry or something, and then you want to generate the pronoun which is he. So this word has to remember that the first name mentioned is a boy. But if it's like really far away, um, the gradients just don't flow. Um, so it does not actually remember what the word was initially. So the gradients tend to vanish with long contexts. So even though it's unbounded context, actually what happens is only the recent words are used to generate the next word, because the words just get forgotten. Yeah, the effect of the words that are in the past are reduced like exponentially almost as we proceed into the sentence. Mm, and RNNs are slow to train uh, because it's not possible to parallelize over time steps. So time steps simply means the words. So each word is like a time step, and the thing here is you can calculate the hidden state at say word 3 only after you have calculated the hidden state of word 2, and for word 2 you would have to calculate the hidden state of word 1. So for word n you would have to calculate n minus 1 and so on. So it's completely sequential. So you can't parallelize it over time steps. So you can't use so it's not using GPUs efficiently. So it's slow training. Yeah, it takes a yeah, it's really slow. Mm, so this is where transformer models come in. So transformers, they got rid of RNNs completely. So I think in between RNNs and transformers, there were a family of models which used both RNNs and attention. So attention is the main thing of transformers. So what transformers did was they got rid of the the recurrent part of it. Um, Instead, they just made it only attention. Um, yeah. So in transformers, you you look at the whole input together at the same time. There is no sequential part of it. Yeah, we'll be going into this in some more detail, I think. So this is the encoder part in a transformer. So encoder is, uh, yeah, you can just think of encoder as, I mean, you are just encoding words into some vector, uh, and this vector has a good context of, I mean, these vectors are contextualized, and you can use it for any downstream task and or anything like that. So essentially what you're trying to do is you're trying to find good representations of your sentence. I mean, that is the encoder part of transformers. Then there's a decoder as well. So usually you have, this is one encoder layer, and you can have a bunch of these. So I think BERT has like 12 and 24. So the BERT medium has 12 and BERT large has 24, I think. Um, so this is the most interesting part in the transformer block, where you have multi-head attention, add and norm, and then this is a normal feed forward. So add is, it's just a residual connection. So if you are familiar with ResNets, I think this is something similar, where having this skip connection allows the gradients to flow much more easily. Yeah, so it just prevents the problem of vanishing gradients. So now we'll just go into detail of what this multi-head attention is. Um, so these are actually explained much better in another blog. I did not go through it, but I mean, I had gone through it. So for those of you who had taken the CS224N course that we had done, we had all gone through that at that time. Uh, yep, this is the one. I mean, there are probably hundreds of explanation of transformers now, but this is the classic one. I mean, I don't want to go through this now because I did not go through it in the recent past. So, but this is a really good explanation of transformers if anyone is like really interested. But we'll go through it now in a brief way. Um, so, uh, so each attention is just a way of um, I mean, what you're trying to do in attention, ultimately the aim is to get a good contextualized encoding or representation of your words. And so essentially a word has to look at its surrounding words to create a good contextualized encoding which represents that word at that location. And the way attention does this is it creates three different projections of every word. So there is value, key, and query. So these three are just three projections of the word vector. So initially you start with a random vector for each word, right? And I mean, that is all trained once you train the whole transformer, but each word has its own vector, and V, K, Q are just projections of that word vector. And I think, oh, sorry. Um, yeah, there might be a good diagram of that here. Please let me know if anything is confusing. Okay, so you have you have a word and each word has its own vector, and then you have a randomly initialized matrix wq, another one wk wv, and you multiply this with this to get q1. So q1 is a query vector of this word, q2 is a query vector of this word, this is the k, this is the key of this word. So you have three different projections of the vector of the vector of vectors of each word. Okay, q1 k1 and v1, q2 k2 and v2. And let's just go back. Okay, I'll just okay. So suppose you're trying to predict the uh, suppose you're trying to predict the representation of a particular word. So you take the query of that word and then you multiply it with or do a dot product with the key of every other word. And the intuition behind this I'll try to explain later. So what you do is you take the query of the particular word that you're looking at now, or yeah, and then you take the multiply it with the key or do a dot product of that with the key vector of uh, every other word, and what you get is essentially a similarity of this word, the current word, with every other word. And then you do a softmax just to get a probability score, and then you get a score for each of the words of how relevant it is to the current word under consideration. And then you get a new representation for the current word by doing a weighted average of the value vectors of uh, every word. So that is how uh, I mean, yeah, that is how the whole self attention thing works. And in the lecture he gave some intuition on this. Let me just, I think I had written it down. um, so so the intuition that he gave, which I found slightly intuitive, was so query could be something like so suppose you are trying to find, suppose the query is a, suppose the word under consideration is a noun or something like that, and the query could be, so so attention, what you're trying to do in attention is you're trying to find, I'll just show that quickly, you're trying to find words which are most relevant to the current word under consideration. So for the word it, here it has high attention scores with animal, because it is a pronoun that refers to the word animal. So that's why the attention score is high. So the intuition that he gives is, okay, so the query could be something like, query is actually representing a question, like give me the previous adjective or something like that. And then uh, so query is a question which says give me the previous adjective, and then key actually represents um the property of a word, which says this current word is an adjective or something like that. So when you multiply q and k, so if that particular word happens to be an adjective, they get a high score. um, yeah, because q is asking for an adjective, and the k of a word which is an adjective, if you do a dot product of them, uh, it will be a high score. And then uh, that particular word gets a really high score in the final weighted average. Yeah, so obviously all of these are randomly initialized in the beginning, everything is randomly initialized. We are not forcing anything like okay, this one should look for adjectives and this one should look for something else, determinants, pronoun co-reference resolution, something like that. All of these are naturally occurring in the process of training. But this is just a way you, this concept of QKV are just ways that you enable this kind of attention to happen. Yeah, this is how you enable something like that to happen in the network. um, so for so there uh, yeah, so here, okay, I'll just read this. Compute key and value for each previous word. Yeah, I already mentioned that. Compute query for the current output and distribution over all the previous words. So with the query, you dot product with all the keys and you get a distribution over the other previous words. So here the next word is unicorn, I think. So for unicorn, the relevant words are actually all of these, uh, because these is, I think it's a pronoun or determinant, I'm not sure. It refers to the unicorns, the unicorns, and silver white is just an adjective for unicorn. Um, so the query could be something like, uh, give me the previous adjective, and the key is just saying, okay, this word is an adjective, and the key of this is also saying, okay, I'm an adjective, but the key of this one would say I'm not an adjective. So when you do a dot product of the query and key, you get a high score between this and this. And at the same time, this is also relevant, so that's why you have multi-headed attention. So the next query, so in, so multi-headed attention is basically parallel attentions happening. So you have different query for the same word, different keys and different values. So in a multi-headed attention, in the next in the parallel attention that happens, the query could be asking for the determinant, give me the determinant, and in that instance this word would be having a high score. So the reason why this is relevant is to predict the next word. If it is these, you know, it's a plural, right? Whereas if it was the, then it would be unicorn. If it is these, it's unicorns. So that's why this word is relevant. And the horned is also relevant because it's an adjective of this. If it's horned, you know that it's probably a unicorn or something like that. Yeah, this was the intuition that he gave for queries and keys. Yeah, but if it's confusing, please do read this blog. It's good. Yep. Um, Attention distribution softmax. Yeah, you do a softmax after that, and then you take a weighted average of the value vectors to get the representation for the current word. I don't know why these slides are repeated. Okay. So multi-head attention is just do this part in parallel so that the same word can attend to multiple words, because there are different types of attention as we have seen earlier, different types of attention that we want to do. But since all of these are done in parallel, it is efficient. mm, Self attention is order agnostic. Yeah, uh, there is no uh, ordering that we have, or there is no order here in the input that we have given. Yeah, it is not dependent on the order of the words. So in order to give it some information about the actual position of the words, we add a positional embedding to the input. So positional embedding is just again, it's something that's slightly complicated. He has not explained in the lecture, but I think it should be in this. Yeah. So it's just a separate embedding that you add, and the thing about this embedding is it is unique for each position in the word, I think. So you're just adding information that represents the position of the word to the embedding, so that it is accounted for. Mm, yeah, and then you have mask as well. So suppose you are having a like a normal language model, you only want to attend to the words that it has seen, I mean that are before it. So if you're attending to the future words, it can just look at the answer and predict that directly. So you don't want that to happen. You only attend to the words that are prior to it. I think the way it's done is you just give a negative infinity attention score uh, to those words. Hmm. All words directly connected. Yeah. So the thing that we have discussed about with RNNs, uh, long term relationships are very difficult because the gradient vanishes. If you, yeah, if you're trying to predict a word, and if that word is very much related to a word that it is that which is hundreds of words ago, that thing cannot happen in an RNN because the gradients get vanished. But in transformers, all words are directly connected. uh, like the 100th word can have can directly look at the second word and uh, yeah, attend to it. And so I mean this totally gets rid of that problem. um, all time steps are computed in parallel. So again, RNN is sequential, so that problem we have gotten rid of here. Self attention is quadratic because you have to compute the dot product of each word with every other word. All time steps can attend to all time steps. So yeah, which is not very efficient, right? So it limits the maximum sequence length because yeah, it is n squared. So you can't have something that's really long. Mm, yeah, I hope all of these was clear. I mean, it does not go into too much depth, but okay, there are other tricks that transformers use. So there's layer norm. So layer normalization is, I mean, it's used instead of batch normalization. So what he said was batch norm is more used in images, and in NLP, layer norm is more of the norm. Uh, so in layer norm, um, it does not depend on the batch size, right? You are just normalizing across the layer. So in batch norm, you just normalize across a batch. So here you normalize across the layer, and this is I mean yeah, it's normalization is used usually it stabilizes training. And I think yeah, he did not give any substantial intuition on why this works. It's just empirical. mm, so warm up is I think it's the increasing, I mean the warm up of the learning rate. I think it starts from 0 and then increases linearly. So that's something they use. These were not introduced for first time in transformers, they were used earlier, but these were the things that worked well in transformers. Inverse square root training schedule. I have no idea what that means. Inverse square. Okay, it's, yeah, I think it's something to do with scheduler, but I don't have much experience with that. Yep. If anyone knows, you can please join in. Careful initialization is just the initialization of weights, and label smoothing is again something that, I mean, not introduced by transformers, but they used it here. Um, so perplexity is, I think, how you judge the. It's a metric for generated text, and lower is better. Yeah, transformers uh, achieve the lowest perplexity at that time. Um, yeah, these are some features of transformers. So one thing he mentioned here, which was interesting to me, is what he said was every time you look at a new word in transformers, it reads every other word in the entire sentence really quickly, um, which is right. I mean, which makes sense because each word can look at every other word, no matter how far it is, and yeah, it can attend to that. Um, so transformers have minimal inductive bias, all words directly connected. Okay, I think we've already read this. It is quadratic. Transformers scale up well. Yeah, I think this. Uh, I mean, we know about this because that's what OpenAI have been doing. So GPT-3 is just a bigger GPT-2. I think. I mean, they have not changed much. Um, they increased training data. GPT-2 uses 2 billion parameters. Recent models is, yeah, I think GPT-3 has 175 billion parameters. So we have crossed this now. Um, Decoding language models. We can now train a probability distribution over text. Exponentially many possible outputs. So we can't output the max. Okay. So we are trying to generate text. We So if we are trying to generate text, we don't know which sentence is the most probable because there are so many possible sentences. So how do you actually decode in a language model? How do you generate words or sentences? Um, so greedy decoding. So in greedy decoding, every time you just take the most likely word. So in a decoder, uh, I mean, obviously, what happens is at each time step, you do a softmax over your entire vocabulary, and you choose the word which has the highest score, and then in the next step, uh, again you choose the word with the highest score. So that is greedy decoding. You just take the most likely word at each time step, and but this does not guarantee that it gives you the most likely sequence. So there might be um yeah, there might be a word that you missed, which gives rise to a sentence which has uh, which has a more probable sentence. So greedy decoding does not give you the guarantee that um, the sentence that you will be getting at the end is the most likely sequence. Exhaustive search is not possible because you will just have uh, you'll just have too many sentences. So it will be too expensive. um, so there is a middle ground which is beam search. Mm, 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 mm. Yeah, okay. So beam search just keeps track of the k most probable partial translations or hypotheses. So it just stores the k most probable generations and score of each hypothesis is the log probability. And yeah, so it's just slightly better than greedy search because you're keeping track of the k most ones. It's not guaranteed to be optimal. Yeah, it's more efficient than exhaustive search. So if you have k is equal to 2, you just keep the you just generate two words, and then you keep the two highest the two highest probability sentences, and yeah, and then you choose the one with the highest probability. I mean, you add all the likelihoods, and the one with the highest likelihood will be the generated sentence. So yeah, I mean, normally what you would do is you just keep the word in greedy decoding. You just generate. I mean, you just remember the word with the highest probability, and then next with the highest probability, and then you continue along that track. But in Beam, you generate two, and then you just keep the two highest sentences. Um, I mean, you remember those, and you continue generating for those. So this one got ended here because the two highest sentences were both happened in this branch. So that's why the generation ended over here. Beam decoding different hypotheses may produce, and so the way you end a generation is when you get the end token, when the decoder produces the end token. When hypothesis produces end token, you can stop expanding and place it aside. Okay.
Yeah, I think that's what happened with those. It encountered the end token, and therefore it stopped.
But if this particular sentence does not come in the top k, you would end it in that scenario as well, right?
Well, my impression was that at each point it expands to k possibilities, top possibilities, and then maintains the graph till the all the end tokens are received, and then computes the best path from there. But I may be wrong.
Okay. Um,
No, actually, you keep only k top candidates. You don't otherwise the graph would grow exponentially.
Yes. Yeah.
Yeah, so you only keep top k candidates. So you
Yeah.
are limited. You are pruning basically, or stopping the less probable branches.
Here k equals 2, therefore it's just 2 at each stage.
sorry about that. I'm just clarifying. So Arto, so you think that this stopped because it was not in the top k, right?
Yeah.
Okay. Okay. When a hypothesis produces n token, stop expanding it and place it aside. Okay. Continue beam search until all k hypotheses produce n token or hit max decoding limit t. Okay. Select top hypotheses using the normalized likelihood score. Uh, 1 by t. No, no. Okay, yeah. You are just normalizing the score because otherwise shorter sentences would always have higher scores, which makes sense. So you want to normalize it for the length of the uh, generated sentence. Um, so this is like something bad that happens in beam search. There is just a repetition of phrase that happens. Um I don't know the exact reason why this happens, but it's just something that's observed in beam search. Does anyone know why this? I mean, what is it in beam search that makes this happen?
I guess the lecturer was kind of giving one possible explanation to this. Uh, so that during training, we do not do beam search. So during training, we like always with transformers, we essentially using like 100% teacher forcing, right? So
Mhm.
we always generate the next token using the reference input. And well, and beam search decoding is actually quite different from that. So sometimes you just kind of the model basically operates in a regime which is different from that during training, and maybe that's why it's kind of collapses to this self-repetition mode.
Hmm. Okay. Yep. Yeah, that's another thing that I forgot to mention. So all of these beam search, uh, sampling, all of these are done uh, not during training, but when you're just generating text from the model, from the trained model. So during training, like Arto said, you do teacher forcing. I mean, yeah, you actually do greedy decoding, right? I mean, you take the highest probability and you train it with that as a prediction.
No, you do teacher forcing, right? So you basically have, what it should do, right? So that's what you send to the next stage in the decoder.
Okay, yep, that's right. Yep.
Yeah.
So, yeah, so since we actually know the labels, you use the true labels and you train the model. Okay. Sampling. Um, just give me a second. Okay. So sampling is when. So what happens in beam search is sometimes you get really generic, um, boring looking and generations. So especially in the context of a chatbot or something, um, the answer, I mean, you get really boring answers. So if the aim of the model is to generate something that looks slightly interesting, then uh, greedy decoding or beam search may not be the best approaches. So sampling is just sample from the model distribution. So whatever distribution you get over the words in your vocabulary, you just sample from that. um, so pure sampling is gives you something like this. uh, Again, sampling does not give you, even though the aim of sampling is to give you something that uh, doesn't seem like a boring response. Sometimes it can be very incoherent, since it's not the most probable sentence according to the model. So sampling can give you incoherent sounding generations. Yeah, and in sampling, once you sample one bad word, then the model is in a state it has never seen during training. So since you're sampling according to the probability distribution, there is a small chance that you will just pick up a word which is just very rare and it has not seen in training. So if that happens once, then the generations henceforth would just might be gibberish. It won't, yeah, it won't be that good. TopK sampling. So I think Mike Lewis said that he was one of the authors in this work. So TopK sampling chooses the top K words in your distribution, and then it truncates the distribution. Yeah, just normalizes it. I mean, truncates and then normalizes and then samples from those top keywords. So this allows for some diversity since you're actually sampling from those words, not just picking the most probable ones. At the same time, since you are getting rid of the ones which are not in the top K words, you are reducing the risk of bad samples. So this gave some improvements according to Mike. Finally, okay. I guess this uh, used all of those techniques. Evaluating text generations, evaluating language models. When you, yeah, evaluating language models is easy because yeah, we just measure the likelihood of the held out data. I mean, since it's like supervised learning, right? So it's not that hard. But evaluating generated text is hard. Trade off between quality and diversity. So I guess what he means here is um, if you're trying to produce diverse and interesting looking output, the sentence quality will suffer and vice versa, right? If you try to focus on quality, the diversity will suffer. Word overlap metrics like Blue and Rouge are obviously wrong but surprisingly useful. So I think these are used for tasks like summarization, translation, and so forth. So it's just simple word overlap. So suppose you're translating, say, French to English, there will be a gold standard of translation which has been done by a human, and you look at the machine translated text and you look at the word overlap. I mean, it's not a simple word overlap. There's a complex formula for both of these, I think. But these are wrong because, as you know, summarization and translation can be done in like hundreds of ways. I mean, there's no single way of writing a summary or a translation. So there are still, this is like a big problem, I think, in NLP, not having good metrics for these type of tasks. New automated metrics have been proposed. Okay. Sequence to sequence models, conditional language model. Okay. Sequence to sequence models is when you have an input sequence and you have an output sequence. This could be translation, summarization. Given a dialogue, generate the next response. Given a question, generate the answer. Okay. So these are all examples of conditional language models. So in a normal language model, what happens is you just give it a prompt, and even if you don't give it anything, the task is just to generate. I mean, you're giving the model free will to generate anything, right? You just generate any text. So conditional language models is, I mean, as it says, it's conditioned on something. Um, okay. Encoder. Yeah. So you have, so this is the encoder and this is the decoder. So you feed an input sequence to the encoder, and so this is the earliest sequence to sequence model by Ilya Sutskever. Um, so you feed it an input sequence, and I think this is an RNN, right? So you have so at the end of the input sequence, it has a vector which encodes or contains information about the entire input. So this is like the this is fed into the decoder as the first step. It's called thought vector for some reason, and yeah, that's fed into the decoder, and then the decoder generates the output sequence. So in this case, it's a translation task. So the decoder module writes output word by word. It generates word at each time step, the translated word. Sequence to sequence transformers. So you have the same thing. So you have an encoder task and a decoder task. So this could be something like you feed in English words here at the input, and you feed in the translated, say, German sentence, the corresponding German sentence. So you feed an English sentence here and the equivalent German sentence here, and it outputs the uh, translation, the prediction of the German sentence over here. So this is actually this part is a conditional language model, since it's conditioned on the input. So here, what happens is you are getting out contextualized encoding or representation of the English sentence. So, and the way you get that contextualized representation is attention, right? Self attention. So each input word attends to all other input words in the encoder stack. And in the decoder stack, um, uh, each input word attends to all input words, all previous output words. Okay. So here the input that you give is the equivalent German sentence, and this German sentence can attend only to previous words in the German sentence. So suppose you're trying to predict the third German word for the translation of this English sentence. You don't want it to look at the third word or the fourth word, right? Since you'll be basically looking at the answer itself. So you will only attend to the previous output words, and then there is the uh, I forgot the term, cross attention. Uh, yeah, the type of attention which is not self. So it can attend to the uh, the English words as well, all of the English words of the English sentence. Um, yeah, so this is a conditional language model. Since we are not just generating any text, it is conditioned on the input English sentence. Yep, I hope that was not too confusing. Yeah, this is like the brief summary of that. Like in encoder stack, the attention is you can attend to all other input words, whereas in the decoder stack, only the previous words you can attend to the output words. For the input words, you can attend to all the input words. I mean, the output word can, when you're generating the output word, it can attend to all the input words. I mean, essentially what that means is when I'm trying to generate the nth German word, I'm only allowed to look at the first n minus 1 or attend to the first n minus 1 German words, but I'm allowed to look at the entire English sentence. And then you can generate the nth word, nth German word. So this is a conditional language model. Mm, transform is big. Okay, this is just talking about the parameters, and the blue score of transformers is, yep, it's much higher than the convolutional models. This is for English to German and English to French. Interesting that the English to French has a much higher blue than English to German. That's I don't know if the reason for that, but it's interesting.
The languages are similar, right? I mean,
Okay.
English and French are both, nicely tokenized, whereas German is compounded. They have these giant words which actually mean 3 English words, sort of thing. So therefore, I think.
Interesting. Okay, this is something that I did not understand. Back translation. Did anyone understand from the lecture? I did not bother to listen to it again, but models are trained on.
Yeah. Actually, this back translation trick is really important, and like the gain in blue score for translation, which this paper which used back translations as data augmentation, the gain there was much higher as compared to switching from the RNN-based attention augmented models to transformers. So here, if you can scroll back a bit to the previous slide, which was with blue scars. So here you can see that we go from some 26 something to 28 something in English to German. And if I remember it correctly, this back translation is a paper which used back translations for data augmentation. They achieved something about definitely over 30, and I think it was closer to 35 blue score. You can go to papers with code and check out it there. I think it's still somewhere around the top on the leaderboard.
And I think the reason why it does that is because you're essentially creating noisy inputs, right? Something like the VAE, it has the additional regularization because of the noise, and it is able to deal with the model is better able, more robust to inputs.
Yeah, that's definitely one factor. But I think in particular that paper, maybe it was because they could use
data volume
much more data.
Yes, of course, that is a big one.
Yeah, but yeah, I think both contribute to the final improvement. Like the translation section should be there. So and yeah, so the idea is you train, you have some parallel data and you can train your model to generate translations, and then you use that model to generate translations for your unparalleled data, like for any data, and then you can search for WMT14 or something.
This one, right? Oh, okay. Yeah, that's the data set.
That should be it.
Back translation at scale.
Yeah. So that's that paper. You see it 2019, and so the score is around 35. And for when the transformer was introduced, the score was in our slides it's 28 something. So that was quite significant improvement.
Could you quickly explain the data part? How does it get the extra data?
So you trained your model to translate on your parallel data, right? And then you can generate the translations for a lot of more data, for any kind of data. You have not parallel data, but but you can generate this translation using your model, and then you can translate back, right? You trained your two models, like English to German and German to English. and then you do so that what you do, you translate from English to German, then translate it back. So you get another sentence, but your German text, like the basically so in this way you can kind of have your labels clean, right? You want for this translation task, you want to have clean labels, and but you can handle a noisy input, right? So we kind of okay.
I got it. Yeah. So basically, the input might be noisy, but the labels are clean because those are normal sentences, right?
Yeah. So you as a target, you feed this original sentences, but you use this back translations as an input, and in this way you kind of so as like first you have some kind of regularization. Yeah, you deal with diverse inputs, and also you can by doing back translations you can use any data. You don't need to have your original data in German.
The other thing he pointed out is if you have a low resource language, so and you want to essentially you can if you want to develop something from English to a low resource language, if you switch it around, you suddenly have tons of input data in the low resource language based on this parallel thing, right? Because you already have this English to, I think he says Burmese here. So English to Burmese, right? So, and that is trained on a small piece of, a small corpus. And then because you have lots of English text, you can auto-translate a bunch of English into a bunch of Burmese text, right? And then use your noisy Burmese text to train your Burmese to English translation.
Yep. Thanks, Sujit and Arto.
Yeah.
Yep. I hope that was clear. That was interesting. Okay. Massively multilingual machine translation. So you train a single neural network on 103 languages paired with English. Massive improvements on low resource languages. I don't know much about these, but you have models like XLM Roberta, and I think even recently there was another model, I think by Facebook, which I don't remember the name, which could translate into multiple languages. I mean, the same model doing.
Yep,
Facebook, right?
this is T4. So this was, let me share the link. So very large model that was released in 2019, I suppose. So this had all the massive how do I say it? Those if we look at the capability of a huge multilingual mod, so this had all the stuff, and there are a couple of how do I say it? GIFs. If you scroll down, yeah, and the data distribution that you can see across the language scores, uh, across the available examples. So here, that kind of a cluster that it formed based on the translations of uh, those groups of languages, that was uh, in, interesting, and this was also alluded to in Google's I/O keynote, uh, 3 or 4 years back, or I don't know. I am confused with the timeline, but this was in one of the keynotes too. So they uh, since they work on the NMT, kind of a translation with a Google Translate. So this kind of a huge language manifold was uh, kind of uh, scaled up, and yeah, it it had a brief mention there. So yeah.
Okay. Thanks, Mike. So I think in this, the bilingual baseline means it's the single language to, I mean, English to that particular language model as opposed to the multi language model. So for low resource language, it says that the multilingual model has actually better scores than the bilingual model. I think that's what they say here. Translation quality comparison of a single massively multilingual model against bilingual baselines that are trained for each one of the 103 language pairs. That's very interesting, right? The multilingual model has higher score than the model trained specifically for that particular language.
I think it has to do with joint learning gains that people have, right? So if you have two targets, like if you make your network, predict one thing versus two things, where you have two labels, they actually reinforce each other, right? So I think something similar to that might be happening here.
Like similar to multitask.
Exactly. Right.
Yeah. Mhm.
Right.
Interesting.
Yeah, and I don't know if that was this paper or maybe next something later, and they use this kind of mixture of expert things when you kind of have separate like this fully connected parts of transformer. There are several of those, and those called like experts, and the data is routed to these experts kind of sparsely. So basically, in this way, the data from maybe we have some low resource language and some high resource language which have similar structure, and those two languages are supposed to be routed to the same expert, right? So to the same network for the fully connected layer, and basically this kind of helps to use this information from higher resource language to learn the weights for lower resource language, right? But also it kind of allows you to preserve this flexibility to treat like different languages differently.
Thanks, Otto. Mm, Visualization of the clustering of the encoded representations of all languages based on representational similarity. Okay. Okay, so the clusterings actually follow the real life groupings of language that we have. That's interesting. Okay. Okay, now we move on to self-supervised learning. How much can we learn about language by just reading unlabeled text? Yeah, self-supervised is the big thing right now. I mean, the most interesting thing. Word to vec. Apparently, it's from 2034. Um, So word to vec is basically you're learning a vector for each word, and vector space representations for words, and it's done from unlabeled text. Um, so intuition related words occur close to each other. Use neighboring words to fill in the blanks. So basically, the concept of word to vec is you look at. I think there was a simple sentence which encapsulated word to vec. I think it goes something like you learn the meaning of a word by looking at the words next to it, something like that.
You will be known by the company you keep or
Yeah,
something like it. Yeah,
yeah, very the same
yeah,
meaning. I mean, yeah,
yeah.
the same concept here as well. Um, the okay, these are learned. Okay, I don't know why they repeat the slide. Okay, so you have a word here, and you want to uh, get a vector that represents this word. So the idea is that you can use the words that are surrounding this particular word and use those to get the vector of this word. So I think what they do here, so initially all words are assigned a vector uh, which are randomly initialized, and then you suppose and then you do it. I mean, you train on the whole corpus that you have. So you take a word, and then you take a window around that word. Suppose three. So you take three words ahead and three words before that particular word, and then you pass those through a neural network. And I think you just try to predict the word that was masked in a way. And I mean, and when that training happens, uh, you essentially end up with good vectors for the entire uh, corpus. All the words in your vocabulary get uh, trained vectors. I hope that made sense. I think that's how word to vec works. So essentially, you for each word in your corpus, you take a window around it of some length, say 2 or 3, and then you try to predict this inner word using these vectors. You have a neural network for that. This is, I mean, it's a simple neural network. Uh, and then, yeah, by training that, you end up with good vectors for each of the words.
Yeah, basically it's the weights of the neural network, right? Which is your word to vec matrix, the embedding matrix. That's what's
Oh, right.
trained, and
Yeah.
that's a side effect. Right? Yeah.
Yes. Okay. Um. So yeah, these are. I mean, we have all seen this a million times. You get interesting relationships with the vectors that you get from word to vec. So the vector for the word king minus the vector for the word man plus woman, the final vector that you get is closest to the vector for the word queen. Yeah, this was at the time this was mind blowing. I mean, because you are just looking at a lot of English text, and you create vectors from those, and those vectors uh, I mean, I mean, the in that vector space there is a concept of gender and all of that. This concept of royalty and all of that, it's all embedded in that vector space, because only then I think something like this would work. Yeah, so this was very it was a very interesting result at that time. Hmm. The word to vec is fast and scalable. Word representations are independent of context. but interpretation of words depends strongly on context. So this is because so once you train a word to vec model, you end up with what you end up with is actually a dictionary, right? I mean a mapping of a word to a vector which is frozen. But usually the meaning of a word uh, very much depends on context. I mean, the common example is words with different meanings, right? You have bank, which has multiple meanings. So you can't just, so the meaning, the vector of the word bank would be just a mixed up version of both meanings, which is not what we want, right? So the actual vector, the actual representation of a word is heavily dependent on context. So that is where things like word to vec or glove fails. um, then you have GPT, the original one. So this contextualized words by just using the left to right language model. So the task is just a normal language model, and you get the actual, I mean, you contextualize words by looking at words from left to right. Pre-train network to predict the next word. So yeah, so once you train the left to right language model, what you get is, so now if you just ignore the final layer which predicts the next word, and you just take out uh, uh, the layer values of the penultimate layer, what you have uh, is like a context contextualized vector for the next word, right? So that you can just use uh, for, you can just fine tune, and you can just change it. I mean, you can add some other uh, network at the end, and you can fine tune it for a task specific loss function. So, yeah, so essentially this is another way of getting a contextualized vector for a word. Yeah, or yeah, contextualized vector. um, so here they are inputting, I mean, they input a review, I think, for a product, and they are using it to classify um, it as, I mean, as classify it as a 5-star review or a 4-star review and so on. So what you can do is you take a trained GPT which already knows how to contextualize a sentence, right? Since it is already trained, and you can just fine tune it by attaching a simple neural network at the end, and now you just train it on a sentiment classification task, and it works just fine. uh, so that was GPT. And then you had something called Elmo. I think this was from Allen AI. So GPT considers only leftward context. So Elmo considers so Elmo has basically, it's a simple architecture, very similar. You have a left to right language model, you have a right to left language model. You do the same thing, but from both sides. So right to left language model predicts the uh, nth word given the n plus 1, n plus 2, etc., given all those words. So now you have um, two contextualized uh, vectors. One represents the left to right one, and one represents the right to left context. So here they just concatenate the final layer output and use it for whatever downstream tasks. But this is just a shallow combination of leftward and rightward context of the word. Since you are just concatenating it, there is no like interaction and anything. So yeah, that's like a disadvantage of this. So um, BERT kind of solves that. So the self-supervised task in BERT is, in BERT you mask a small percentage of words in your sentence, and then you try to predict that sentence using the words in the whole sentence. So this is similar to word2vec in that way, but the difference here is you have a large transformer network, right? You where you have attention and contextualized vectors, and using that, I mean, you attend to all other words, and then using that you predict this word. So this is the sentence here is Bert is a golden yellow muppet, and you predict the word Bert. I mean, you feed this whole sentence to a transformer, and the task of the transformer is to predict this word and this word given this input. So these two are just masked inputs. So mask is a particular type of input that BERT takes, and the task of BERT in the pre-training step is to predict the mask token.
So in this case, your bank, if you use the word bank in two different sentences where it had different meanings, the embeddings for bank as a result of the BERT encoding would be different, right?
Yeah. Yes.
Yeah.
Yeah. So I was just thinking, the initial embedding. So there is a even in BERT you start off with an embedding matrix, right? Of word to vector. So in that embedding matrix, there is just a single vector for the word bank, right?
Do you pass in a sequence? Probably do. Yeah.
Yeah. But then at the end you have a
No, you don't.
contextualized.
Yeah, you don't. So the embedding you don't control basically. It's there. It's some random weight inside, but over time the language model, will get trained by seeing different sequences of inputs.
Yeah, so basically you transfer not only the word vectors, but also like this BERT itself contain these weights. They contain an information how you like mix the information in or combine the information in these vectors to produce a contextualized word vectors, right? So the contextualized word vectors are produced as we flow through the model, right? And I guess kind of related to that, there are those papers which show the attention patterns, and in early layers, usually attention is like more broad, and in later layers, it usually like more sparse. And so basically you like take this this first embedding layer, right? It contains a dictionary of tokens and vectors. And then the model kind of combines those to produce a contextualized representations, right?
One other difference is that with word2vec, you can basically take the matrix out and just use it as a static thing that you can run embeddings through. Whereas in case of BERT, you need a trained model, right? You cannot take out the weights, right? You basically have to, infer using that trained model.
Well, why not? You can use embeddings from BERT and try to
But which
those.
embeddings would you use? I mean, that's the point, right? I mean, it has multiple layers, so you cannot just extract.
Yeah, you can only use an embedding layer, right? So there is some vocabulary in BERT. It's like 30,000 something tokens.
Right. Yeah.
you can take those and use it instead of word2vec.
Oh, I see. Okay, okay. Generate them and okay, okay. But that's still static. It's not context dependent anymore.
Yeah, and then I don't know if it would be better or worse compared to word2vec, but in that case it would be no different conceptually.
Exactly. Right. Right. Yeah.
Okay. So this is the improvement that BERT gave over the human performance. So Squad is the question answering dataset. So this is the score by humans, 91.2, and BERT was able to overtake that. And Glue is the it's a benchmark of I mean it consists of a set of NLP and NLU tasks, and yeah, BERT came close to, I mean kind of close to the human level scores. This was the previous state of the art at that time of, I mean at the time when BERT came out. And like I said, so the pre-training task in BERT is mask 15% of the tokens, and then you predict those particular masked tokens, and all words condition on all other words. So yeah, you are allowed to attend to all other words. So yeah, the purpose of such supervised learning tasks is you are not actually interested in this task. You are just trying to, it is just a way for the model to understand how language works, how yeah, that's essentially what the thing is. You want to learn a way to produce good contextualized encodings of the words in a sentence, and this is just a way of this is how the model actually learns English in a way. So Roberta was an improvement on BERT by Facebook. So they just simplified BERT's pre-training objective. So I think what, I'm not sure, but I think BERT has another task along with this masking, which is next sentence prediction. So you give it two sentences, and BERT tries to predict if the first sentence follows the second sentence follows the first sentence. So this is I mean it's another way of trying to understand language basically. So I think Roberta removed that, if I'm not wrong, and yeah, they just scaled up batch sizes and more compute. It gave um, significant improvement over BERT in Glue and Squad. These are I think models in the family of BERT, slightly different. XLNet from Microsoft, I think, predict mass tokens auto-regressively in random order. Okay, span BERT predict. I mean, it masks spans instead of tokens. Electra substitute tokens with similar ones instead of masks, and predict which tokens were changed. Albert tie weights across layers. Okay, XLM is the translation one, I think. Run BERTs on lots of languages. So
I had a kind of off-topic question. So for autoregressive models, I've been curious. I mean, so we talk about left to right, right? I mean, but what about languages that read right to left, like Hebrew or Arabic? You know, does XLNet also read right to left, or you know? So that's the. I don't know if anybody knows. Just asking. Yeah.
I don't know, but I would suspect you got to feed in order of like how it reads, not how it
yeah.
how you.
Okay, I see. Okay, so you would also send it in that same direction sequence. Okay, got it.
Yeah.
That makes sense.
Yes.
Mm-hmm. Pre-training for NLP, a lot of objectives work well. Crucial to model. I mean, yeah, pre-training. I mean, there are many tasks that you can that count as pre-training. This, I mean, the aim is to just learn how language works, right? And the aim is to use get as much knowledge as possible from English text without using any kind of labels. It's crucial to model deep bidirectional interactions between words. Large gains from, yeah, I mean, as we know, bidirectional interaction is important, bidirectional representation is important.
Yeah,
Large
about
gains from,
that bidirectional representations. So he stresses that it's important here. But on the other hand, like GPT-3, it's autoregressive model. So it kind of like it does not use like this right context for predictions, but it's also quite successful, right? So
maybe they should try BERT at that scale, right? We have not done
yeah,
that yet.
that would be something probably, but yeah, interesting.
Okay. Yeah, and we have been continuing to see large gains from scaling up pre-training, and they have not seen any kind of stagnation yet. So yeah, that seems to be the thing now. Just scale up the resources and parameters. So BART and T5 are uh, models for conditional generation, pre-trained for conditional generation. So these are models that generate text. BART pre-training seek-to-seek models by denoising text. Pre-training for conditional generation. BART. I think I may have missed this in the lecture. Does anyone know what how BART works?
Yeah, pretty much as it shows here. You
So it
basically
tries.
have, yeah.
Okay, it fills these blanks but it generates the whole sentence. Is that how it works? Like,
That's your label. So you train this entire pipeline. So I think of it as a BERT encoder, BERT encoder, and an XLNet decoder, or any autoregressive, in fact, right? So, and then you basically train it with masked sentences, and you try to make it predict, right? So you train it to predict the full sentence, and that's how you would. You now have like a sec-to-sec model, which is transformer based.
so how is it different from just uh, using a BERT model and then just writing the sentence as is? I mean, with BERT model, you know what this blank is. You can predict this blank and this blank, and then I can just put the sentence together myself.
That is true. Yeah. Well, I think BART has some special use cases, which I don't know of, though, honestly. I've read about it, but that's about
it's much I think it's better for like sequence to sequence tasks, like summarization, abstractive. So you cannot really do this abstractive tasks out of the box with BERT, right? Say if you want to like do question answering, you will be able easily extract the span from some context to answer the questions, but you wouldn't be able to generate an answer which is not in the context.
abstractive stuff.
Yeah.
Okay, got it. Okay.
And yeah, so this 6-to-6 model work for that stuff.
So this won't be the only pre-training, right? Because this is obviously not abstractive. So is
I,
the fine tuning how you learn summarization and all?
I'm not sure, but I think the idea is that because you have this autoregressive thing, that is what it can dream up, alternative ways to express the same concept, right? So I think that's the reason you have this autoregressive decoder part.
Okay.
Yeah, and like in BERT, it's not ready like from the start to do some task. You need to fine tune it, but yeah, but it's like much easier to fine tune a good language model again. The same logic as with BERT applies. So basically, you have right now with this BART model, you have a good language model as decoder and a strong like bidirectional language model as encoder. And with that combined, you do fine tuning on some kind of basically any kind of task, and you can do it.
Okay. But pre-training synthetic models by denoising text. Yeah, denoising is, I think it refers to the of words in between. And new state of the art on summarization, dialogue, and abstractive question and answering data sets. Yeah, this, like Arto had mentioned.
Right.
Okay. I think we have reached the end. So these are some open questions. How should we integrate world knowledge? Yeah. So yeah, usually when we write text or communicate with someone, we assume that the other person knows a lot about the world. We assume that he knows, like he has common sense, and that is how we communicate with each other and write text. But the machine obviously does not know that. So this can lead, I mean, this is why a lot of we see a lot of obvious errors and silly mistakes that the machine makes, because it does not have the world knowledge that we have. So how do we integrate this world knowledge with the model? That is a big question. How do we model long documents? Bird-based models typically use 512 tokens. Yeah, here since transformer models have n squared, the complexity because of the attention, that is one problem. And I think of recent there are so many solutions around this. I think like sparsification of the attention, attending only to the close words and things like that. I think there are some models like long former, linear linformer and things like that, which have reduced the complexity of the attention, which allows us to model long documents. But I think the problem is still there. How do we best do multitask learning? um, I think what it means is using the same model to do two totally different tasks. Can we fine tune with less data? Are these models really understanding language? Yeah, these are like the big questions that still exist in NLP. Anyone has any interesting points to add in this? Please do so if you have anything to add.
One aspect I was thinking, and there was a question on this too, and the lecturer basically kind of dodged the question, I think. But basically, for image fine tuning, you typically freeze some of the layers, right? But in case of transformers, you typically don't, right? So that was something interesting. I thought, is it like a difference, right? Yeah. Although there are experiments which, where they have tried to progressively freeze. There is one, I think, called ELSA what would ELSA do, right? So where they basically freeze the large portion of the layers in the transformer, and they still got up to 90% of the performance that they would have gotten otherwise by not freezing anything. But the common practice seems to be for fine tuning. In case of transformers, don't freeze anything. Whereas in the image case, where you do ResNet fine tuning kind of thing, where you typically freeze a lot of the layers already.
Yeah, I was gonna experimenting a bit with it, and always results are better, or at least the same when you fine tune the whole model. Yeah, maybe in some cases, I think the results were better when I kept the embedding layer frozen, but that might be just noise or some really small data set, something like that. So I'm not sure about it. But and also this was discussed in I think it was in FastAI Discord, and there was this opinion from Sylvan Gauger. I'm not sure how his surname is pronounced, but now he works at Hugging Face, and and he is one of the authors of, together with Jeremy Howard of FastAI. So he said that they at Hugging Face they also do this. They observe that this fine tuning the whole unfrozen model works better, and so his explanation was kind of like. So that's kind of his probably intuition, not quite a complete explanation, but he says that probably this when you fine tune this frozen model, it kind of finds some region in the loss landscape, and which is suboptimal, and then the model cannot get away from that region to better regions when you unfreeze it. So
yeah, okay.
That's something interesting, but also basically it's kind of empirical thing there. I don't think there is some kind of theory behind this.
Okay, thanks, Sujita Nato.
Sure.
And yeah, I think this Hugging Face has also released the GPT-3 Neo, I think in the last few days.
Right.
If you guys are interested. So this is the open source GPT that was done by this company, Eleuther AI. I have not read too much about this, but yeah, it's now available on Hugging Face. Okay, yeah. And the parameter size is like much smaller than the actual GPT-3. So this is the Eleuther AI's replication of the GPT-3 architecture. Yep, this might be something you can try this weekend. Okay. Yep, the summary training models on lots of database explicitly modeling linguistic structure. Yeah, this has been noticed for the last few years. Architecture should compressing sequence through bottlenecks. Okay. Okay. Models can learn a lot about language by predicting words in unlabeled text. I mean, this is essentially what the whole BERT family does. The pre-training step of BERT. That is how you learn. I mean, that's how these models learn a lot about language. Fine-tuning for specific tasks is then easy. Yep. So this two steps is like the backbone of most NLP these days. Bidirectional context is crucial. Yep. Okay. Yep. We have come to the end of it. I think we have taken up a lot of time. Are there any questions before we end? Or anything to share? You can share it in Slack or any links. I mean, if you have, you can share it in Slack. Are there any questions?
I have something to share. I'm writing it out in the Slack. So it's not, related to this. It's kind of related, but not related. But okay. So yeah.
Okay. Okay, I'll just copy all the links and paste it in
Yeah.
Slack.
Yeah.
Okay, if we don't have any questions, thanks everyone for coming and listening for 2 hours. Thank you. Bye bye.
Absolutely. Thank you, Gautam.
Thanks for the links.
Cheers.
Yeah. All right.
Bye.
Bye.
Thanks, guys. Take care.